Welcome to our Mechanics of Solid class 2. Here today we are discussed about two topics, that is first one, bar of uniformly varying cross section. That means a bar of uniformly varying cross section subjected to an external load and its properties. Then second case is that a bar subjected to self-weight. That means when due to its weight some deformation takes place, and you discussed about that two topics. Okay, then first of all, first to go through the first segment, that is bar of uniformly varying cross section. Here consider this bar. It is varying cross-sectional areas and the diameter changes from D1 to D2, and external load P is act on this bar, and due to this load there is any deformation takes place in this beam, in this bar. Then you have to find out what type of elongation takes place and how do you find that elongation. For that, let's consider the figure. Let P be the axial pull on a bar of length L whose diameter varies uniformly D1 to D2 as shown in figure. It's already given here. Some more markings are here. You can see that Y as a small element considered at a distance x from the end D2. Okay, D2 diameter end. Then a small length dx along the lengthwise direction. Total length of the beam is L. At a distance x there is a small elemental L dx, and the radius of that segment is considered as y. Okay, small element. Consider an elemental length L dx at a distance x from the smaller end and radius y. Here first of all we take that y in y and express that y radius in terms of d1 and d2. Then from this figure we can see that d2 by 2 plus some amount of extra length, we can add it, we will get the value of y. So you have to find that extra small elongation, a small variation. Therefore the d2 by 2 is the up to this we can find the d2 by 2. Then after that the varying due to that variation there is some amount of increment. Then you have to find that increment. So from this we can find d2 by 2 plus that increment value. Then that increment value you can find from the making that segment like this, d2 by 2, then this y, and at a distance x. Then you can find that small increment in terms of x and L. Therefore that small increment is equal to d1 minus d2 by 2 multiplied by this x by L. That is this y value is related to or varying proportionate to the d2 minus d1 by 2. So you can make that expression like this, then d2 minus d1 minus d2 by 2 x by L. So we will get the radius y as this term. Here next we consider that d1 minus d2 by L, take it as a constant. For the time being it will be take it as a constant. So the equation again we will reduce to like d2 by 2 plus k by 2 into x. Then next step you have to find that small area. Small area is equal to, when radius is given, then we can find that area, cross-sectional area in that radius, that is pi r square. Here pi, then r is our y, then replace that r value as d2 by 2 plus k by 2 into x all square. From that relation you will get pi by 4 d2 plus kx all square. Then next step we have to find the change in length of that differential element, that is dx is the small length. Due to this external load the length will increase, and that small increment of this length ds will be delta dx. You have to find that delta ds using our equation, that is stress strain relationship, that is PL divided by AE, where P is the external load, it's given. Then dx is the elemental length. Then delta is the area of that elemental length. Then E is the Young's modulus. Then substitute the values of dx and A all in this equation. We will get 4p dx. 4p means area expression. You will get this. Then this 4 comes up, and then 4p dx divided by pi d2 plus kx whole square into E, where substitute delta A value here. You will get like this. Okay, this is the small increment of that segment. Next you have to find the complete increment, that is how totally that segment is elongated. Then find that thing. You have to integrate that value, small increment, up to that limit. Okay, so PL by 4p by pi e into dx divided by d2 plus kx whole square is the small increment. Then change in length of whole rod is equal to delta L of that whole rod. That is previously we find the delta dx, that is the small increment. Then we want to find the total increment is equal to 0 to L 4p by pi e into dx divided by d2 plus kx whole square. Then after integrating 1 by x square term minus 1 by x here, therefore d2 plus kx, k is a constant, 1 by k, 0 to L, apply the limit, then L, apply the upper limit, kl plus d2, then lower limit 0, this becomes 0, then you will get 4p by pi e minus 1 by kl plus d2 plus 1 by d2. Here after getting this equation, you can substitute our k value as d1 minus d2 by L. Substituting these in this equation, d2 cut, and you will get 4p pl by pi e d2 minus d1. Here again d1 minus d2, you can cut that values. Then you will get the expression delta L is equal to 4pl by pi e d1 d2. 4pl by pi e d1 d2. This is the expression for elongation of a bar of varying cross-sectional area when external load P is axially on that beam. Okay, then same equation when the variation or varying cross-section is uniformly varying, it has been uniform diameter. Then what happened if the bar has been of uniform diameter d throughout? It's become delta L is equal to EL. EL means E is equal to sigma by E. Area, you have the area, then P value, sigma P by A, you can rewrite, then E is equal to sigma by E, then later we will get 4P by pi d square E. Here total elongation is equal to this E multiplied by total length, that is equal to 4PL by pi E d square. This is similar to our this expression. Here we will get d square, but here d1 d2, that is the only difference between these two. Then next one, this is our first portion. Then today's second portion is a bar subjected to self weight. Self weight means when a bar having its own weight for time, for later due to that weight some amount of increase in length takes place. You have to find that amount of how much it will increase, and how can you find that value. So for that you will derive an expression for that. First of all, consider a prismatic bar of cross-sectional area A and supported as shown in figure, loaded with the self weight only. Here this is our bar and there is no external load, the only its weight is acting on that bar. Therefore consider a small element at a distance x, and dx is the small elemental length. Then total length of the bar is L and the bar is fixed at C. Okay, here for equilibrium, here P is the weight of, let P be the weight of the body, then P is balanced by the supported end. Okay, then first of all consider a section x is at a distance x from free end. force px act at xx, force ps acts at xs. Consider a section xs at the here. Then here we know that some amount of force is acting on this. Then how do you find that force? That force is created by the weight of the body below that points. So the weight of the body up to x is the force. So px is equal to weight of length dx up to dx. There is some amount of material, and that weight of that body will give the force. Okay, then how do you find the weight of the body? Already we know that gamma be the unit weight of the material. What do you mean by unit weight? Unit weight is nothing but weight per volume. It is similar to density. Density is mass by volume, but unit weight is weight by volume. Then weight by volume, you have the value of that unit weight, or every material have its own unit weight or density. Then you can from this value is known, you can find the weight of this segment. That is, unit weight multiplied by volume will give the weight. Okay, so unit weight multiplied by the volume. Unit weight is already known. Then next we want to find the volume. Then here this is our segment, and x is the total length. Then area of cross section, let it be A of this small segment. Then that area of cross section multiplied by distance x will give the volume. So the expression is equal to ax gamma. Then this is the force acting. Next you want to find the stress. Then we will get the force at this section x's. Then you can find the stress. Therefore the stress is equal to P by A, that is equal to ax gamma divided by A, that is x gamma. Then maximum stress due to the self weight of the prismatic part of the length L at C is equal to, stress is related to length. Therefore when x become maximum, the stress value maximum. Maximum x value is possible up to L. Therefore L gamma is the maximum stress. That means that due to this weight, the maximum stress is produced at this point C. Here next step, you have to find the elongation. Now elongation of the element dx at x is equal to, you want to find the elongation, you have the expression PL by A. Here Px is the load, replace the L as dx and area of cross section and Young's modulus. Therefore the total elongation is equal to integral 0 to L, this equation. Then substitute the values, P as Ax gamma, then dx divided by area into E. Here gamma and E are constant, we can take it outside. Then cut it from both up and down. Then you will get 0 to L x dx, and integrate x square by 2 0 to L, you will get gamma L square divided by E. That is the total elongation of the bar due to its weight. Here we can see that the total elongation is related to its unit weight and Young's modulus. When Young's modulus is increased, the length is reduced. Then similarly, weight is increased, its unit weight is increased, its elongation also increased. That is proportionality. Now this is the expression connecting unit weight and Young's modulus, length, etc. Then elongation in terms of our weight, we can rewrite, we can multiply it by top numerator and denominator by area. You will get A into gamma L square divided 2AE. Here A gamma L is equal to A gamma X, or L is equal to its weight. Area multiplied by L give the volume, then gamma is the unit weight. Then AL gamma become weight of that segment, WL divided by 2AE, where A gamma L is the total weight of the material. Therefore the elongation expression is equal to gamma L square by 2E or WL by 2AE. This is the expression for the elongation of a part due to its self-weight. When W is the weight, then the delta value is equal to WL divided by AE. So go through the derivation and write down it's in your notebook, and do the problems related to this topic.